Topic 2.3 is all about exponential functions. So now we're going to focus mainly on just the shape of this function and leave the relationship or the differences between linear and exponential for a little bit later. But an exponential function is a kind of function you studied in Algebra 1 and Algebra 2. Here's what they look like. We have exponential growth and we have exponential decay. So we have to talk about the characteristics of these graphs. Exponential functions, by the way, are functions that actually show up a lot in the real world. They appear in many places, including population growth, money growth, like when you tell a bank to hold your money and they give you money back for that, called interest, that grows exponentially. Radioactive decay, the spread of disease, if you become a forensic scientist, the rate of the body decaying, all of those things, that all has to do with this type of function. So an exponential function has the general form, f of x equal to a times b to the x power. B is my base. We talked about this last time. B represents the base. That's why it's b. We can also call it the common ratio if we were talking about a geometric sequence. Or you'll see some people refer to it as the factor of the exponential function. So it's growing by a factor of 2, growing by a factor of 3. You'll see that word. We're talking about the base there. The a value represents the initial amount. That is going to be your y-intercept. So maybe that's more helpful to see that this is your y-intercept. When we're graphing it, we're looking exactly on the y-axis to identify what number to put in place of the a. Now, there is no, like, air quotes, parent function for this type of data because your base changes each time you change the base and the shape changes. So this is just called the general form. There's no parent function here, but there's parent functions for individual bases, if that makes sense. So let's talk about what these two values do for you. If you have exponential growth, your a value is going to be above 0. For most real life examples, probably 99.9% of all real life examples, the initial value is going to be bigger than 0. So if you notice for both growth and decay, the a value is bigger than 0. Mathematically, it can be less than 0. But in real life, most likely it's going to be positive, so it's above the x-axis. For exponential growth, your base, your b value is going to be bigger than 1. So a number like 2 or 5 or 1.5. Those are all numbers that are bigger than 1, which makes our graph grow. It's going to get bigger and bigger and bigger very, very quickly. On the other hand, exponential decay, the base is going to be some number between 0 and 1, so some sort of true fraction. For an exponential function as opposed to a sequence, your b value is always going to be positive. So there's not going to be a negative number in your base placement. It's always going to be some positive number. A sequence can have a negative common ratio, but an exponential function will always have a positive base. Okay, we see that growth goes up and decay goes down. Do those words sound familiar to us? Great, let's add some precalculus terminology to this type of function. So when we studied exponentials, we added the new vocabulary of increasing versus decreasing and concavity. We're going to apply those vocabularies to these functions, but we can see based on, I don't know why I keep moving this around like crazy, based on the shapes. For increasing and decreasing functions, the answer is real easy. The exponential functions are either always increasing or always decreasing. So we either have always growth or always decay. Since they will never switch from increasing to decreasing, what that means for us is that we have no local extrema, no relative extrema. There's never going to be a maximum or a minimum value because it never changes from increasing to decreasing. Also, if you look at those shapes and we were to make our concavity hands, you would only use one shape, either concave up or concave down the entire time, which means that exponential functions are always concave up or always concave down, and they never switch from concavity to concavity. That tells us that exponential functions have no points of inflection. So we know what the shapes look like. We just need to be able to describe them using the precalculus terminology of increasing, decreasing, concave up, and concave down. We also need to be able to talk about the end behavior of these graphs. And we're going to do that in a limit statement. So these limit statements aren't necessarily always going to be positive and negative infinity like most of our rational functions were. In fact, they can't both be one of the infinities. For exponential functions in general form, as the input values increase or decrease without bound, the output values will increase or decrease without bound, or they will approach 0. Because we have horizontal asymptotes for these graphs, we know that we're going to get close to but never touch that x-axis, the line y equal to 0. So if we look a little more detailed at these limit statements here, for this growth graph, as x decreases without bound, what is the graph getting closer and closer to? So if I'm looking this direction, what's the graph getting closer and closer to? 0, the x-axis, so a flat line at 0. For my growth equation, I don't know why that didn't change to yellow. We'll just make this yellow. I didn't mean to make that orange. Okay. My bad. Stick with orange then. Okay, if we look at the growth equation as x approaches positive infinity, what's happening with the output values? They're increasing. So as we increase our x values, we are increasing our y values, so the right side end behavior goes to infinity. For a decay graph, it's like it switches. Because since decay is going down, when we look backwards and we decrease our x values, our graph is actually going up. So our left side end behavior is infinity, but our right side end behavior is approaching that horizontal asymptote of 0. So we have these boundaries on the bottom or on the top if it's reflected of these functions. Okay, so our first step today is to successfully write these limit statements. Now I'm going to say this because I graded y'all's quizzes right before fall, not quizzes, your tests right before fall break, and there was a limit statement question on there, and there are still people not writing our limit statements in the correct way. They have to look like this. I know in Algebra 2 last year you could write it as a string of numbers. That's not going to work anymore. You have to stack it because it needs to be an actual limit statement, not an arrow statement, which is what that one's called. Okay, so stick with the notation I'm showing you. This is a hard and true thing. If we're writing the limit statement here, we want to look on the left and on the right of the graph. Pretty easy. If you notice on the left, what is the graph approaching? 0. So we, what word did I just say? The limit as x approaches negative infinity for this function, we'll name it f, would be equal to 0. I have to have the limit statement stacked like that. So be sturdy with yourself and make sure it looks like this. The limit and the x approaching the infinity should be on top of each other. F of x, or the name of the function, is big, and then equals the number. On the right side, what's happening with this function? It's going up, so it's reaching towards what number? I heard it. Very good. All right, that is what the limit statement has to look like. Don't make it a string. It needs to be stacked. Okay, so I said earlier that 99.9% of real functions have a y-intercept that is above the x-axis. I still stand by that statement. But in this mathematical problem here, what do you notice has happened to my y-intercept? It's negative. It's like I've reflected the graph. So this is still a graph of exponential decay. It's just been reflected. Because if I were to flip this over, it would be getting smaller, going towards the x-axis as x's increase. So if I flip it over, it's still technically decay. But I'm reading the graph here, and on the left side, as x approaches negative infinity for this function, we'll also name it f of x. It didn't give us a name. What is the output? What are the output values approaching? Negative infinity, because it's going down. This probably won't happen in real life, but mathematically we can reflect this graph over, so it's an option for us to view. On the right side, as we look, as the x's approach positive infinity or increase without bound, what is this function approaching? 0. All right, so we've got the limit statements pretty good. But what if I don't give you a picture? No, don't quit. If I don't give you a picture, all you need to do is look at the initial value and the base, meaning I need to focus on this number and on this number. And we think about what kind of function is created from those two numbers. Okay, I'm hearing some good stuff. Is this going to be growth or decay? Why is it going to be decay? What's less than 0? Actually, it's not less than 0, it's between 0 and 1. So we're looking for less than 1, but still positive. So it's between 0 and 1. I drew this graph kind of crooked, so I'm going to do that again. So if we see, we know this is going to be decay. Is my y-intercept going to be above or below the x-axis? Above. So I could sketch this graph, and it would look something like this. Where we have, I used the wrong color there, where we have a y-intercept above the x-axis at positive 5, we're pretending that's 5, and I know it's going to decay. So just from knowing those two things, I can, one, sketch the picture for myself, which makes it easier to write the end behavior, or I would just know that it is a above the x-axis decay function, which means my limit statements here on the left, the limit as x approaches negative infinity for this function named g of x would be equal to what? Positive infinity, yes. And on the right side, the limit as x approaches positive infinity would be 0. Very cool. So you don't have to have a picture or even graph the function with a calculator to be able to tell the end behavior. We can just use that initial value and the base to match up if it's growth or decay. Easy peasy? Tentative, yes. Okay, great. Let's look at the back kind of question. We're still describing these kinds of functions. Now I just want you to use the vocabulary of increasing versus decreasing and concave up versus concave down. Don't overthink it. This graph, is it increasing or decreasing? The output values are going down, so it's decreasing. Is this concave up or concave down? Concave up. If you were making this shape with your hands would be touching at the wrists. That's a concave up graph. So very good. This is a decreasing concave up graph. It will never change. There are no maximums or minimum values. There is no points of inflection. There are no points of inflection. I swear I speak English. Okay, what about this one? Is it increasing or decreasing? Decreasing because it's going down. But is this concave up or is this concave down? Interesting. So we do see that if we were making the shape with our hands, our fingers would be touching instead of our wrists. That's concave down. But it is decreasing the whole time. It will never change. Now, just like on the front page, what if I don't give you a picture?
Quit.
Don't quit again, Chewy. So we just got to look here at the initial value and the base. The initial value here tells me that my graph, is it going to be above or below the x-axis? Above. So I'm going to make some coordinate point here be 3. Does the base being 4 tell me this is growing or decaying? Growing. So we should have some sketch that looks like this based on that graph. And once I see a cute little sketch of this graph, I can answer the questions. Is this one increasing or decreasing? Increasing. Is this concave up or concave down? Concave up, because our wrists would be touching if we were making this shape, but it would be the increasing portion of concave up. Now, we're going to advance our question abilities here. The next few questions, well, number 3 is not free or multiple choice, but the examples 4, 5, and 6 are AP level, AP style multiple choice questions for this topic. But this one, number 3, kind of ties in together all of the table things we've done for forever. Because this question now, unlike the questions you did on your quiz, is not just, is this linear or exponential? What's the other thing we have to check here? Quadratic, which means we're going to have to do a little bit of work with this table to eliminate all of those options. So I recommend when we're doing these kinds of questions and you see all of the options listed for you, especially when we add a 4th option later, we're going to start by just checking the average rate of change. I see that this has equal length input value intervals, it's plus 5 every time. So I can just check the differences here. How do you go from 3 to 5? How do you go from 5 to 9? How about from 9 to 17? How about from 17 to 33? Okay, so is this going to be linear? No, because the rate of change is not constant. But since we have to check quadratic, we check the changes in the rate of changes. How do I go from 2 to 4? How about 4 to 8? Oh, not times. We're always, with linear and quadratic, we're doing adding and subtracting. And then, so is this going to be quadratic? No, because the change in the rate of change is not the same. So we're back to the drawing board. It was not linear, it was not quadratic. We have to check exponential now. So we go back, and I'm just going to do this backwards like this. How do you multiply to go from 3 to 5? You can. It's 5/3. It's 0 to a number. You can't multiply anything to make 0 become any other number. It will stay 0. But how about from 5 to 9? It'll be 9/5. Automatically, is this going to be exponential? No. So we've eliminated all of the options. It was a lot more work than it had been in the past because we have to check both the differences, the second differences, if it adds cubic in there, the third differences, and whether it changes by a proportional value, which means that this function f could be neither, I guess not neither, it should be none of the above because there's more than one option, none of the above. Because over equal length input value intervals, the output values of f of x, and let's list all of the reasons, do not change at a constant rate. That's linear. They do not change, do not have a constant change in the rate of change. And do not change proportionally. Proportionately. Nope, I missed a letter. So when it's none of them, we give all of the reasons. Bless you. We have to prove that it's entirely wrong for me. It's a lot easier to prove because you can say it's not this, it's not that, it's not that. Bless you. Okay. That's a lot of words, so I'll slow down for a second. But the next 3 questions on this paper are multiple choice style questions that you might see for this topic. Okay? We like describing graphs in this class. Talking about the characteristics and key identities of a function is very important for pre-calculus skills. So example 4 says the function f is given by f of x equal to 5 times 0.7 to the x power. Which of the following describes f? Okay, so if we're looking at the multiple choice questions here, our first job is to decide if this is growth or decay. Which one is it? How come? What is less than something? The rate, the base, the factor, is between 0 and 1. So we know it's not going to be the 2 answer choices that talk about growth because we know that this is going to be decay. But then we need to start talking about its end behavior because if you see, the answer choices are giving you 2 options for the end behavior on the right side as x approaches positive infinity. So for me, I think it's helpful, again, like we did in the other ones, just to kind of sketch what this graph would look like. I know it's decay, but is it going to be decaying underneath the x-axis or above the x-axis? Above, very good. Because this 5 is a positive number, our initial value is somewhere up here. So our sketch would look something like that. Which answer choice should we pick? A is correct. Because as x's increase without bound, our function is going to get closer and closer to that horizontal asymptote, y equal to 0. Okay, bless you. Your turn. Example 5 is for you. Let's see if we got it. In example 5, it says the function f is given by f of x equal to 2 times 3 over 2 to the x, which of the following describes f. So same situation. I look first at the answer choices and I see I pretty much need to choose between growth and decay first. So based on this ratio, based on this base, is this going to be growth or decay? This one is growth. That fraction is 1.5. It's bigger than 1, which means I'm going to get rid of the 2 options that say decay. I don't even want to look at those anymore. I know that it's growth, and now I need to decide what type of growth it is, or what the shape of growth looks like. Now, since this is a 2, wrong color. Is this going to be above or below the x-axis? Above. So if we have growth from above that is not reflected over the graph, this is what it looks like. So as x approaches positive infinity, what's happening to my output values? They're also going to positive infinity. Did we get it? Yes. Sweet. Did anybody read example 6 while you were waiting for me.
I read it.
I read it. It says the value of 2 times 2 times 2 times 2 times 2 times 4.7 is the output value of an exponential function a times b to the x, where a and b are constants. Which of the following describes the function and an input value that corresponds to this output value? If we were to condense this output value down, meaning I were to take all of this business and simplify it, how many times is 2 being multiplied there? 5 times. So I could rewrite this as 2 to the 5th power times 4.7. If I just reorder these so that it matches the formula I have written on the paper, I would have 4.7 multiplied by 2 raised to the 5th power. This now matches the regular basic version of an exponential function, which means, what is my initial value here? 4.7, so we're going to get rid of a and b. It also means that I have a base of what? Great, can't eliminate anything there. What is my input value? 5. My x is the 5. So my input value, what we plugged in, was 5. You are right, we do have PSAT practice today. Thank you so much, Chewy. Okay, so